Now we're going to move to more complex organic molecules. Up to this point, we've looked at hydrocarbons, things containing just carbon and hydrogen, and structural variations thereof. But now we're going to introduce other atoms. In particular, we're going to look at oxygen, sulfur, nitrogen. Those will be the big changes. And so this leads to fairly dramatic changes in the properties of the organic compounds. So to begin with, we start off with the idea of heteroatoms and alkyl groups. A functional group is an atom or a group of atoms that has a certain set of properties. And it turns out that families of functional groups, like alcohols, which have an OH group on them, tend to have similar physical and chemical properties. Their solubilities, their densities, their chemical reactivities, and so forth. So it's very important to be able to look at a compound and recognize the functional groups, and that allows you to very quickly start to estimate what sorts of properties will be involved with that molecular structure. So heteroatoms are atoms besides carbon or hydrogen when you have an organic molecule. Most commonly, we're going to be dealing with oxygen, nitrogen, and sulfur. But it turns out the halogens, fluorine, chlorine, bromine, iodine, as well as phosphorus are also very important. Now, as you know from our discussion on valence electrons and covalent bonding, each heteroatom will have its own associated characteristic number of valence electrons and correspondingly number of covalent bonds that it will tend to form. And when we're looking at saturated systems, generally the heteroatoms form a number of bonds which is 8 minus the number of valence electrons. So this is a key. So here we can see in this table we have the various atoms, the number of bonds they form, and the associated lone pairs for the systems. So of course, carbon has 4 bonds, has 4 valence electrons, and does not have lone pairs associated with it in any organic compounds. Hydrogen, on the other hand, has 1 bond and no lone pairs. Now, oxygen and sulfur, which are in group 16, they have 6 valence electrons, so they tend to form 2 bonds, and then they will have 2 associated lone pairs. Nitrogen and phosphorus, which are in group 15, with 5 valence electrons, form 3 covalent bonds and have 1 lone pair. And then the halogens, fluorine, chlorine, bromine, and iodine, with their 7 valence electrons, tend to form 1 bond for saturated systems. And then they'll have 3 associated lone pairs on the heteroatom. So here are a couple of examples of structures that you're going to need to be comfortable looking at. Okay, so you can see on the right hand, for example, hopefully when you look at this, you can very, very quickly see that there's an alkyne here. So the leftmost terminal carbons are in a triple bond formation, so that's an alkyne. You can also see in the middle of the structure there's a carbon-carbon double bond. So you can see all the carbons on here. So you can count your way across 1, 2, 3, 4, 5, 6, and then a 7th on the very far right side, 7 carbon atoms in the structure on the left. And then you can see on the right, hopefully you can recognize some of the hydrocarbon pieces. Right in the center is a benzene ring. So there are 6 carbons associated with a benzene ring, and then 1 more carbon in the upper northeast, so on the upper right-hand side. So these are line angle formulas. We don't show the hydrogens attached to the carbons, but we do show the hydrogens that are attached to the heteroatoms, because these can be more variable, so that's important. And so you can see, we've got a variety of heteroatoms on here, and we'll talk about some of these later on. Now, another nomenclature we have is what we call R groups. And an R group generally is what we call is an alkyl group. So like a methyl group would be an R group. A methyl group an ethyl group, propyl group, a butyl group, and so forth. So this is just a shorthand notation because it turns out that the heteroatom very often is the driver for the chemical reactivity for the system. We know that alkanes are relatively unreactive systems. They're actually pretty inert. And alkenes do have addition reactions, and so they're a little bit more reactive. But in general, hydrocarbons are not highly reactive systems. It's their heteroatoms that kind of confer a lot of their reactivity. So here in this figure, for example, we've got what we're going to call an ether. And on the top part of this figure, you can see we have a methyl group, CH3, on the left-hand side, singly bonded to an oxygen, which is singly bonded to a propyl group on the right-hand side. So we can write this as ROR, where here we recognize R represents methyl and R prime represents propyl. And that allows us to have a shorthand notation and also to focus on the ether portion of the molecule, which may be particularly important for a particular application. So if there are multiple R groups, you can often will put a prime or a double prime, or you'll put a number associated with like R1, R2, R3, or so forth. Our first functional group we're going to look at are alcohols. These are very important. So a hydroxy group is the functional group that consists of a hydrogen atom covalently bonded to an oxygen atom. And of course, you know oxygen needs 2 covalent bonds, so it's only got 1, so the other one's going to have to attach to an organic compound. When you have that, when you have an OH group there, you have an alcohol. So an alcohol is a class of organic compounds that have carbon bonded to an OH group. Methanol is the simplest alcohol, so you've got carbon with 3 hydrogens and 1 OH. So we can write the structure of an alcohol as ROH using our R nomenclature. So for methanol, for example, R would be a methyl group. And so R in general represents that alkyl portion of the molecule, and OH represents the hydroxyl functional group. So it turns out that the properties of the alcohol come from that OH portion. That's the big driver. And here are a couple of very common alcohols, which I'm sure you have. In fact, I'm certain that we've all handled these at some point. The one on the left is ethanol, and ethanol, of course, is the alcohol that some folks consume. While it is toxic at low levels, its toxicity is relatively low. But it's also used as a disinfectant. And so here, it's very commonly used with hand sanitizers. During COVID, that was a big thing. So the alcohol-driven systems. Alcohol is a really good antibiotic, so that'll kill bacteria. And then we've got 2-propanol. This is what's used for alcohol wipes. That is a toxic alcohol, so you do not want to drink that at all. So, like we said before, alcohols are toxic. And while the alcohol that you drink, ethanol, is toxic, if you drink it at low levels, then the toxicity is, your body can tolerate it. There are some people who have trouble with that, and we'll discuss that later on. But other alcohols are actually much more dangerous. So, for example, methanol, which is sometimes called wood alcohol, is highly toxic. If you drink it, you get blindness and death. It's one or the other, neither of which is good. That's what's added to make alcohol denatured. So we know we've got an OH attached to a carbon, but we can do this in a variety of different ways. And we have 3 big classes of alcohols. What we call primary alcohols. That is when you have an alcohol group, an OH group attached to a carbon that has 2 hydrogens or 3 attached to it. So 2 hydrogens in an alkyl group or 3 hydrogens. That's a primary alcohol. A secondary alcohol is attached to a carbon that has two other alkyl groups attached to it. So over in our figure here, you can see this is, as we'll see later on, it's called something called isopropanol or 2-propanol. It has two methyl groups attached to that carbon that holds on to the hydroxide group. And then there are tertiary alcohols where the carbon that's attached to the hydroxyl group has three different alkyl groups, or three alkyl groups, they could be the same or different, attached to it. And it turns out this changes the chemical reactivity quite substantially depending on what environment the alcohol is in. So we'll go through naming and then look a little bit at kind of structural and reactivity and physical properties. So first up, how do we name these? Well, the systematic naming of an alcohol is built off of the hydrocarbon name, so the alkane name that you've worked with, except your final E is dropped off and you add an OL. So if you have ethane with an OH on it, you call that ethanol. And then we've got another example here in version A, figure A, the hydroxyl on the terminal group, you have, that's a propane chain, so we call that propanol. For chains with more than two carbon atoms, we have to delineate where that hydroxyl group is. We have to be very clear. We have to indicate the position of the hydroxide group, and we use a number to do that. And of course, we set it up such that the parent, and so just like we did with alkenes, we choose the chain that contains the OH group. And that is our main chain. And then we number that chain such that the OH has the lowest possible number. So for example, C here in this figure, you can see that the longest chain is a 4-carbon chain. The OH is attached such that we want to make that number 2. So this is going to be a derivative of 2-butanol. And in this case, you can see that there's a methyl group attached to position 3, so we would call this 3-methyl 2-butanol. Now there are common names for alcohols. Like I said, earlier, methanol is sometimes called wood alcohol. This figure here shows isopropyl rubbing alcohol. You don't usually see that so much. You'll see isopropyl alcohol or rubbing alcohol. That's 2-propanol. So there are some other common names that you'll see. There are cyclic rings that contain OH. These are very common. They're important for a lot of natural products. They occur in nature and plant derivatives. That plants have a lot of alcohols in their molecular structures, and there's a lot of drugs that that have alcohol moieties in them, or alcohol functional groups. So if we have a cyclic alcohol, we simply treat it just like the alkane, but now we add OL on the end to it, take off the E. So cyclohexane, shown in figure A, when we've added an OH, we call it cyclohexanol. So now that we've done this, then we recognize that the OH now becomes the 1 position for the ring. So in figure B here, you can see that the methyl group is opposite the hydroxyl group. So we would correctly name this 4-methyl cyclohexanol. Diols are important, and so hopefully you can figure out very quickly from the name what a diol is. A diol is a compound that has 2 hydroxy groups on it. And there are a number of these that are very important. There are some that have 3 groups, and they're called triols. Your body actually, a lot of your lipids are based off of that structure. So diols with hydroxy groups on adjacent carbon atoms, that is, carbon atoms that are next to one another, we call those glycols. And there's a very important common one I'm sure you guys have all handled. That's ethylene glycol. That's the primary component of antifreeze. they typically add a dye to antifreeze. So it turns out ethylene glycol is a colorless liquid. The unusual color is usually something else that is added to the system. For a systematic name of a diol, add the suffix diol to the parent, and then just tell the numbers of where things are located. So, for example, ethylene glycol, shown up above, using the IUPAC naming system, we would call that 1,2-ethane diol. Now, the physical properties of alcohols are strongly affected by the OH group. So even you could have a big molecule like hexane, where you've got lots of atoms, and if you stick an OH on there, you radically transform that molecule. And the reason this is because the intermolecular forces in alcohols are driven by that OH bond. An OH bond is quite polar, much more polar than a carbon-hydrogen bond. And an OH bond can do something called hydrogen bonding. And we'll talk about that in lecture a little bit more. We'll probably add in a section on intermolecular forces. But the key point is OH looks kind of like water, doesn't it? OH is a part of the water molecule. So you can imagine, since we said before, like dissolves like, alcohols dissolve in water. Hydrocarbons don't dissolve in water, right? Alkanes, alkenes, aromatics, simple hydrocarbons do not dissolve in water. Alcohols are water soluble. And the oxygen has lone pairs on it, so the OH connect is a hydrogen bond donor and a hydrogen bond acceptor. And so they mix well with one another. Alcohols mix together quite nicely, and they also mix with water very readily. Smaller alcohols are what we call miscible. That is, they completely dissolve in any proportion in water. Now, again, because of this OH group, it causes hydrogen bonding, which is a strong intermolecular force. This causes the melting points and the boiling points to be substantially elevated relative to the corresponding hydrocarbon. So the water solubility increases dramatically, and the boiling point and the melting points all increase dramatically. So like we said before, here's a picture of methanol in water. You can see the water molecules are the red and white three-ball structures. And then methanol, using this sort of space-filling model, you can see that has a darker ball with 3 hydrogens and then a red ball with 1 hydrogen. So that's our methanol molecule. And so this OH group is the real big driver in their solubility. Methanol is miscible in water, so you can mix any, 100% methanol all the way to 100% water, and any proportion in between, they'll mix perfectly. Now, generally, as the hydrocarbon chain on the alcohol gets longer, the solubility in hydrocarbon solvents goes up. So the molecules with more hydroxy groups have more hydrogen bonding. So correspondingly, if you've got a diol or a triol, you're going to find out that the melting point and the boiling point and the solubility in water all increase relative to having just one OH group. The more OH groups, the more hydrogen bonding, the higher the melting point, the higher the boiling point, and the higher the water solubility. Now let's look at the chemical reactions of alcohols. And one of them, we've kind of already talked about this, and that is the elimination reaction. So remember when we talked about alkenes? Alkenes, in the presence of an acid catalyst, can add water to form an alcohol. And if you take an alcohol and you heat it up with an acid catalyst, you can lose water and split that off and form an alkene. So elimination reactions remove water from an alcohol and results in the formation of an alkene. So since we're eliminating water, sometimes we call this a dehydration reaction. And we can, of course, do the reverse. We can take this reaction and run it backwards, and under the right conditions, we can add water to an alkene to produce an alcohol, and that's called the hydration process. So we got dehydration and hydration. Another important reaction is combustion. You know that alcohols burn. Of course, you know ethanol is an additive in gasoline. It's added generally to increase the oxygen content in places that are prone to photochemical oxidizing smogs. And so oxygen is added just to facilitate, or the alcohol is added to facilitate complete combustion. So alcohol vapor is flammable, and in the presence of oxygen and a heat source, we get combustion. And if we do complete combustion, we get carbon dioxide, and water as our product. And generally with the oxygen, you tend to get more complete combustion. You have a lot less carbon monoxide produced and sooting. Alcohols have substantially less sooting flames. So we know that the alcohol can be written with the OH on the end. So here we've got a balanced case. 2 methanol molecules plus 3 oxygens gives 2 carbon dioxides and 4 waters. And you should be able to balance the combustion reactions for other alcohols too. Now I'm going to kind of harken back to a reaction class we had in basic chemistry, something called redox. So we had acid-base reactions. One of the other things we looked at were redox processes, where you change the oxidation number on atoms in a molecule. And here we have an alcohol, and if alcohols undergo oxidation, they typically do this in 2 steps. But the first step, which is the most important, forms something called an aldehyde. And we'll talk about this in our next chapter on carbonyls. But you can see here we've got an alcohol, and the little bracket O just indicates we've got an oxidizing agent. So if we do oxidation, we lose water, or we lose hydrogen in some manner, and then we produce an aldehyde. Organic oxidation reactions, you can have gain of oxygen atoms, loss of hydrogen atoms, or both. And gain of oxygen atoms would be oxidation. Loss of hydrogen atoms would be oxidation as well. Organic reduction is generally the loss of oxygen atoms or the gain of hydrogen atoms. So it turns out this is where the primary, secondary, and tertiary structure of the alcohol becomes important. For a primary alcohol undergoing redox, we see the following process. So the alcohol, primary alcohol has that terminal OH group, and they react in the presence of oxidizing agents to produce a compound with fewer CH and more CO bonds. So really we're going to lose an OH, we're going to lose a CH, and then we're going to make a CO double bond. So the oxidizing agent over the reaction arrow indicates the presence of the oxidizing agent. The primary alcohol starts off with 1 carbon-oxygen single bond, undergoes oxidation to form the aldehyde, which has a carbon with a carbon-oxygen double bond. And it turns out aldehydes, they tend to oxidize pretty readily. So if you've got conditions to oxidize an alcohol, very often the aldehyde will just quickly go on to form what we call a carboxylic acid. And that's shown in the figure here. You take your primary alcohol, you oxidize to the aldehyde. And again, we haven't introduced that structure, but we'll introduce that in our next chapter and talk about it in detail. We're forming a carbon-oxygen double bond. And then if we oxidize that further, which is usually very easy to do, we get a carbon-oxygen double bond and a COH single bond. So now you can see carbon has 4 bonds, 3 of them are to oxygen, and that's a oxidized system. Your body has enzymes, and enzymes are what we are catalysts. They are biological catalysts to carry out some process. So when you take biological chemistry, you'll learn about these catalysts. They carry out all the reactions that go on in our body, all metabolism, catabolism, and so forth. Now, the ethanol in alcoholic beverages is metabolized in your body, and it produces an intermediate aldehyde. It produces ethanal or acetaldehyde, as we'll see later on. And the enzyme that does that in your body is something called alcohol dehydrogenase. And then next, the aldehyde has to get converted to the carboxylic acid, and that's used with an enzyme called aldehyde dehydrogenase. So that's ALD and ALDH. So ethanol goes to acetaldehyde with ADH, and then acetaldehyde to acetic acid with ALDH. And your body, of course, can tolerate the acetic acid, and it can metabolize that or excrete it without problem. But it turns out acetaldehyde is not good for your body. It's actually toxic. And it says here, it's one of the causes of hangover symptoms. It's also one of the causes of liver sclerosis. And it turns out that people who have a fast alcohol dehydrogenase process in their body or slow aldehyde dehydrogenase can actually run into serious problems with drinking alcohol. It says here that they find drinking unpleasant. They generally don't become alcoholic because it's very difficult for them to drink alcohol. It can become very toxic to them because they build up acetaldehyde. In fact, this is the basis of what's called Asian flush syndrome. It turns out that 50 to 60% of people who are from China, Korea, Japan, and that part of the world, they are genetically predisposed to having lower or slow aldehyde dehydrogenase, substantially reduced, and that's problematic for them. Secondary alcohols, they have their OH group attached to a carbon, which has attachments to one hydrogen and two other carbon atoms. When you oxidize a secondary alcohol, you get another carbon-oxygen double bond, but in this case, you produce what's called a ketone. So a ketone is different than the aldehyde. The aldehyde, the carbon had a alkyl group and a hydrogen group. The ketone has two alkyl groups. And it turns out that ketones are not susceptible to further oxidation like the aldehydes are. You can oxidize ketones, but you can't oxidize them using the same pathway you see with an aldehyde. So there's just a single step process here. The secondary alcohol goes to the aldehyde. To the ketone. That was error. It goes to the ketone. Okay, so this is a summary here. It turns out tertiary alcohols do not undergo oxidation unless you do combustion reaction. So the primary alcohol tends to oxidize quickly, readily to an aldehyde, which can oxidize on to a carboxylic acid. A secondary alcohol oxidizes to a ketone, and that's a terminal reaction. The tertiary alcohol does not oxidize. So as we said before, enzymes can degrade ethanol, and it turns out that there's a common application for this. These are breathalyzer tests, which you may have seen. They contain an oxidizing agent, and the oxidizing agent happens to be something called dichromate, and dichromate has an orange color. We talked about dichromate in basic chemistry. I know that was a while ago, but CrO4 2- is your chromate, and Cr2O7 2- is your dichromate. And it turns out in the presence of alcohol, this dichromate acts as an oxidizing agent, and as the oxidizing agent, it gets reduced down to a green chromium-3 structure, which basically shows the presence of alcohol in your breath. Because if you drink alcohol, the alcohol does not oxidize immediately. It's a slow process. And in your liver primarily, you get your alcohol dehydrogenase, which converts it to the acetaldehyde or ethanal, and then, of course, further oxidizes it to acetic acid. Turns out it's not really a quantitative test. It's only semi-quantitative. So that ends the first half of this chapter. We have a number of functional groups to cover, and in our next video, we will march through the remaining functional groups in chapter 13.